Okay, welcome back. In this lecture, we are going to look at the concept of alignment gaps and methods to score those gaps in the alignments. So far in the previous lectures, we have covered several methods for pairwise sequence alignment. This includes edit distance based formulation, then global alignment based formulation, approximate pattern matching, as well as local alignment. And you have seen that these different methods are useful for different types of applications. For example, the first two methods were useful for global alignment. The approximate pattern matching was useful when you have a short pattern to be aligned in a very long text. And finally, the local alignment, where we were seeking local similarity patterns between two strings. So far, we have managed to solve all these problems in quadratic time, that is order mn, where m is the length of first sequence and n is the length of second sequence. For this lecture, the topic will be defining the alignment gaps. I will motivate the need for why do we need to have gaps in the alignment objective function, and then we will see appropriate ways to score these gaps, and within that we will see the most popular way, that is a fine gap penalty system. So, let us start with the definition of what do we mean by gaps in an alignment. So far, if you recall the alignment scoring system that we have been using so far. So, remember that, so suppose we have two sequences as an example. Now, I can define their alignment of both sequences in this manner. So, this is an alignment of both sequences, in which let us say there are 3 matches, then you have 4 space characters, 2 matches, 1 mismatch, then 3 matches, 4 space characters, 1 match, and so on. Now, the method that we have used so far to score this alignment is very simple. That is, we look at individual columns of this alignment and we just check how much do we value and match, plus then a match value between A and A, then a match value between A and A, then the score for aligning character C to a space character, and so on. So, this is basically we are considering each of these columns independently, and then we are adding these score values up. Now, this is a very simple way of scoring the alignment, and this is a good way to start when we are studying this topic. For this lecture now, we are going to introduce the concept of a gap. Now, a gap is nothing but a maximal consecutive run of space characters in a single sequence of a given alignment. So, for example, in this case you have this as a gap where you have a consecutive run of 4 space characters occurring on the second sequence of the alignment. Then another gap is this consecutive run of 4 characters, and there is another gap consisting of a single space character only. So, together we can say that this alignment has 3 gaps: gap 1, gap 2, and gap 3. So, considering this, let us look at another example. Here you have 2 sequences again, right, and again you can see in this time you have an alignment where you see 4 gaps. So, the first gap has 3 space characters, the second gap has 2 space characters, and the remaining 2 gaps have 1 space character each. Now, the explicit reason for showing this alignment is that, observe that in this case the last 2 space characters, that is these 2 space characters, occur in consecutive columns. However, they occur in different sequences. So, the first one is occurring on the upper sequence and the second one is occurring on the lower sequence. So, therefore, we are calling them as two different gaps, because as per our definition we are explicitly saying that it is a consecutive run of space characters in a single sequence of a given alignment. So, together we can say that this alignment has 4 gaps. Now, I will motivate why we are giving this special attention to these gaps, like what is the importance, why do we need to define these gaps in an alignment, and why do we need to treat them differently. So, it turns out that it would be useful to incorporate gaps in our scoring system to obtain alignments that are consistent with biology. Let me give you a concrete picture of why am I saying that. So, just to recall, remember that in our introduction module we have said that if you look at genomes of 2 human beings, they are going to have some differences between them. So, for example, in this illustration I am showing you a substitution of character C to character T. Now, there are various kinds of mutations that can happen. There can be substitutions, insertions, deletions and many other type of variations that happen in reality. Now, typically when we do sequencing of a genome, we would, let us say, take a blood sample of a patient and then we will run it through a whole genome sequencing protocol. Now, the goal of the whole genome sequencing is to know the genome sequence of that individual. So, ideally what we want as output from a sequencing machine is one sequence per chromosome. That is, if I have, let us say, 23 pairs of chromosomes, then I would want one sequence, the entire sequence for each chromosome, and that will give me ideally my complete genome sequence. However, in practice that does not happen. So, typically when you do whole genome sequencing, due to various technological limitations, what we get as output is millions of short sequences that are fragments of the genome. So, the length of these sequences can vary from 100 to 1 million bases depending on the technology being used, but ultimately you will get these fragments of genome sequence, and now it is up to us to understand what mutations were there in the target genome which I had sequenced. So, now one way to analyze what mutations might be there in the target genome would be to take each read that was given by the sequencing instrument, take each of those reads and align it to a reference genome. So, for example, we can take this read and align it to the complete reference genome, and there the alignment will reveal some differences. So, for example, we may not get exact 100% match of the entire read. We may see in the alignment that maybe there are some mismatches and maybe there are some space characters occurring in the alignment. Now, we expect that such alignments will reveal the true mutations in the target genome. So, for example, this particular difference in the alignment may be occurring due to the substitution mutation that has happened in the target genome, right. Similarly, this particular consecutive runs of 5 space characters may point to the fact that maybe there is a insertion of 5 characters in the target genome. So, in this case actually it is a deletion of 5 characters. So, in this case the characters G, T, G, G, A are deleted. So, what we want as the optimal sequence alignment, that the optimal sequence alignment should reveal the target mutations that we want to study. However, observe that these optimal alignments can differ based on how we score matches, mismatches and so on, because ultimately we are solving an objective like a combinatorial optimization function, and depending on what input we give in terms of the scoring system, the optimal alignment can differ. For example, if I have a match score of 1, mismatch of -1 versus having a match score of 5 and mismatch of -6. Both of these are going to return me different optimal alignments. So in that sense, choosing those scoring systems carefully is very important, so that what we get as sequence alignment are actually reflecting the true mutations in the target genome. Now let us take an example of one example where this scoring system changes the way in which we observe the alignments. So imagine that we have a target genome in which there is a large deletion of 228 characters. So there is a mutation in which 228 characters are deleted in the target genome. Now in an ideal alignment, what we would want is that if we look at the reads that are sampled from this particular region of the genome, we would want that such reads should align to the reference genome and they should reveal a consecutive run of space characters, so that I know that these 228 characters in my genome are missing, that is, they are deleted. Therefore, they should point to a deletion mutation in the target genome. Now this is the ideal output that we want, but now what we get as output from a aligner will depend on what scoring system have we set there, because the aligner will give an optimal alignment based on the optimization function we set. So therefore it is we have to set the optimization function carefully, so that we get such kinds of alignments. And you can see that this is a single gap now. So this is a gap containing 228 consecutive space characters. So what it turns out that how we consider these gaps in the alignment scoring function will determine the accuracy of these alignments. So for example, if we use an aligner with a good scoring system which also takes into account such gaps, then what we would end up achieving is that we will see many reads that align to the reference genome, and we will see consecutive space characters in the alignment that reveal that true mutation in the target genome. So here I am showing you a visualization tool which visualizes the read alignments to a reference genome. So it's a method to visualize many alignments together and how they are aligning to the reference genome, and this particular way of visualization is used to denote the space characters in the alignment. So what it is showing is that most of these alignments are revealing a consecutive run of space characters of length about 228. So this is good, this is what we want, because this is how we will know that the target genome has a true mutation. Now it turns out that if we use a bad scoring system which does not account for the gap scoring properly, what ends up happening is that you will see an alignment where you do not see those consecutive space characters anymore. So there you see some matches, some mismatches, it is a mix of everything, and as a result we will not be able to see the true mutation in the target genome, that is the 228 base pair deletion that we wanted to see. So the purpose of this example is to show that the treatment of gaps in the scoring system is very important, and only then we can see large insertions or deletions properly in a target genome. And there are many other reasons and many applications in which you would think of gaps. For example, if I am aligning RNA-seq reads to the reference genome, again I would need to carefully treat how I am scoring each gap. So with this motivation in mind, let us come back to the methods for gap scoring. So far I have motivated the fact that the gaps should be considered in the scoring scheme to obtain an alignment that is more biologically plausible. So let us understand what scoring system can be appropriate for scoring a gap. So, here I am showing you an example of 2 input sequences, and I am just showing you 2 alignment examples. So, this is alignment 1, that is between these 2 sequences, and this is another alignment possible between these 2 sequences. Now, the question is, which of these alignments do you think is more biologically likely? Is the left alignment more biologically likely, or is the right alignment more biologically likely? Well, you can expect that maybe if this was the alignment, then what it says is that the second sequence has occurred or has evolved from sequence 1 by having 4 short deletions. So, you have 4 deletions in left example, and in the right example you have a single deletion of 4 characters. So, biologically a single mutation is more likely to happen than 4 deletions located nearby to each other. So, as a result we can say that the alignment 2 is more likely, because this can be explained by a single mutation event, right. So, that is but one example, but if you recall our original alignment scoring method, where we were considering each and every column of the alignment and then analyzing the score of the alignment, then it turns out that if we do not consider gaps in the scoring function, then we would end up giving equal score to both of these alignments. So, for example, in both of these alignments you see that there are 6 matches in both cases, and you see that there are 4 space characters. So, both alignments have 4 space characters, and here also you have 4 space characters. Whereas, so if you go with a simpler scoring system, then both alignments will be given equal score. So, the optimization routine will not be able to distinguish which one of the 2 is better, and that is where we have to introduce a better scoring system which also considers the gaps into account. So, for example, in the left case there are 4 gaps, whereas in the right case there is only 1 gap. So, as a result we need a better scoring scheme that also considers gaps in the formulation. So, let us see what may be the possible ways in which we can penalize a gap of length k. One way may be that maybe we penalize based on the length of the gap. So, for example, maybe we can set a penalty which is proportional to the gap length. So, for example, it can be any constant times k, for example, right. Is that good enough? Will that solve our problem that we were addressing before? Well, it turns out no, because if you do that, then if we give a alignment score which is proportional to the length, then we would end up. So, suppose this is, we say that the alignment penalty is some constant times k, then in both cases we would end up having same penalty. That is, in this case you will have you would have c plus c plus c plus c, because you have 4 gaps each of length 1. In the right hand side case there is a single gap of length 4. So, that would be c times 4, which is again equal to 4c. So, in both cases we are ending up with same alignment score. So, that may not be the best way of scoring a gap. What are the other ways? Well, maybe we can solve this particular issue by maybe giving a constant cost to each gap. So, what about irrespective of the length of the gap, we give a constant penalty to each gap. So, that would resolve this particular example, because in this case the penalty would be 4c for this left example, and penalty would be c for right example, because each gap is penalized with a constant, and here there is a single gap. So, therefore, we penalize it by c, and in this case the right example would be favored by the alignment scoring system. However, there is another issue that if you consider this example, in this case the sequence ATC will have equal alignment score with sequence ATTC, as well as it will have equal alignment score with sequence AAG AAA TTC, because in both cases you have 3 matches and I would penalize C because there is a single gap. In the right hand side case also there is a single gap, so I would penalize C. But we see an issue here that the sequence ATTC is more closely related to sequence ATC, yet both alignment scores are equal, which is also not good. So, we need some way in which we are also taking into account the length of the gap as well. So, we cannot disregard the length of the gap completely. So, a better solution, as you can imagine, would be to combine both of these aspects and have a affine function where the cost of a k sized gap is some constant plus k times some other constant. So, this is a affine function in which you say that each gap of length k would cost C1 plus k times C2. So, basically you are charging a penalty for that gap, a fixed penalty, that is C1, and depending on its length you are charging additionally C2 for each depending on per unit length. So, in typically, as you can imagine, maybe C1 can be a larger value than C2. So, C1 can be 10 and C2 can be 2. So, this would resolve both the situations here. So, in this case this alignment would be favored compared to the right hand side, and in the above example you can see that the right hand side example will be favored because there is only a single gap. So, this motivates why we need a better scoring scheme for penalizing gaps, and we will be working with the affine function, that is C1 plus k times C2. One way to interpret this affine function is that for each gap that we have in the alignment, the interpretation of C1 is that C1 corresponds to starting a gap. So, for example, if you are starting a gap, then I would penalize C1, and then for each space character that is there in the gap, that is the length of the gap, then I would penalize C2 for each extension. So, that will be C1 plus 4 times C2. So, we have a fixed penalty for starting a gap, that is C1, and then depending on how far you extend further, we are going to penalize C2 for each extension. And this method is now commonly used in most of the sequence alignment tools, because this addresses the issues that we discussed just before, that it favors those alignments that are biologically likely. So, now we have defined a scoring system which is more appropriate for penalizing gaps. The natural question that comes next is, how do we find an optimal global alignment using the above gap cost function. So, with this gap cost function, how do we solve the alignment problem now? Because we have not considered this function before, we have only so far we have considered scoring systems which do not consider gaps. So, how can we develop a dynamic programming method which aligns two sequences using this new gap cost function? Let us look at that. Let us first address, can we use the same recursion strategy that we have used before? That is, when we did not define gaps, we were just looking at matches, mismatches, insertion of space characters. Can we use the same recursion strategy that we had before? Well, if you think about it, remember that when we were defining Vij, we were having three possibilities, right, depending on how the alignment ends. And then we were saying that the Vij can depend on Vi minus 1j if you want to end the alignment with a space character on second sequence. Similarly, the Vij can depend on Vij minus 1 if you want to have a space character on the first sequence. Can we use this same scoring system now? Can we use the same recursion strategy? So, we have a revised gap cost function now. So, we have to consider this gap cost function in our formulation. Can we use the same strategy as we used before? Well, it turns out no, because now when we are considering this gap symbol, that is that when we are considering this space symbol, we need to know whether we are extending a gap or whether we are starting a gap, because if we are starting a gap, then we would penalize C1 plus C2. If we are extending a gap, then we would penalize only C2. Therefore, this exact same recursion strategy will not work now. We have to be more clever in how we solve this recursion. So, to compute Vij, we need to check whether a new gap is starting or whether we have already started a gap earlier. So, the same strategy will not work. So, what can we do? How can we revise our recursion so that we can still solve this problem efficiently? It turns out that we can use a new trick, in a sense that we have to capture more information in our dynamic programming tables, so that when we are computing Vij, we know whether the gap was started before or are we starting a new gap now. And for that we are going to use 4 matrices, that is we are going to use 4 tables instead of 1 table. So, previously we were working with only 1 table in our dynamic programming formulation. Now, we are going to use 4 tables, and I am going to define what each table means. The good news is that we will still be able to solve the problem in order mn time. That is the same time that we had used for solving the simpler problems with simpler scoring systems. So, let us see how this algorithm is going to work now. As usual, as before we have solved this problem, let us consider alignments of prefix of sequence A and prefix of sequence B ending at j, because that is how we have been identifying the sub problems for dynamic programming. So, we are going to look at all possible alignments between prefix of A and prefix of B. So, remember that some of these alignments will have last character AI opposite to character Bj. So, some of these will have AI and opposite to Bj, and that is how some of these alignments will end. Some other alignments will have AI opposite to space character in their last column. Finally, the remaining alignments will have space character aligning to Bj character, and these are the only 3 types that we have. So, these are the only 3 possibilities for the alignment. Now, what we are going to do is we are going to say let Gij, so I am going to define this term Gij, let Gij be the score of the optimal alignment among all alignments that are of type this one. So, among all alignments of this type, let Gij be the score of the optimal alignment. Similarly, among all alignments of this type, let Fij be the score of the optimal alignment. Finally, among all alignments of this type, let Eij be the score of optimal alignment among alignments of this type. Now, it will become clear why we are defining these notations, because now what we are going to do is we are going to maintain multiple tables. So, we are going to recurse for G, F, E simultaneously, and we are going to classify alignments based on these three types. Finally, the last notation I want to have is Vij, where Vij is basically the standard score of optimal alignment between prefix of A and prefix of B. So, this is considering all possible alignments, that is the optimal alignment score between A1 to I and B1 to J among all possible alignments. So, naturally, if you think about it, Vij is basically equivalent to maximum of Gij, Fij and Eij, because alignment can only be of one of these three types. So, if I am looking at the optimal alignment, then Vij has to be maximum of Gij, Fij and Eij values, right. So, I hope these three definitions are clear now, because these three definitions are going to be important on how the recursion will work. So, let us look at how we are going to work out the recursion. As I mentioned before, we are going to work with 4 tables. So, we are going to fill 4 tables in our dynamic programming, that is G, E, F and V, and we are going to fill those 4 tables together, and when it comes to recursion we have to fill these 4 elements now, that is Vij, Gij, Eij and Fij. So, we have to recurse on these 4 values, and once we have filled the entire 4 tables, at the end we are interested in outputting Vmn, because that is the optimal alignment between complete sequence A and complete sequence B, right, based on the definition that we had. Okay. So, let us understand how are these recursions going to work. Let us start with the simplest one. So, Vij is nothing, as we said, is just a maximum of all these 3 values, because Vij is the optimal alignment between suffix of A and suffix of B. There is no restriction further. So, V is maximum of all these 3 values. So, what about Gij? Well, let us recall what the Gij meant, right. So, Gij, remember that we were talking about the alignments of type in which the last column had Ai character opposite to character Bj. So, we are specifically looking at alignments of this type, and Gij is equal to score of optimal alignment among alignments of this type. So, how can we define the value of Gij? Well, we know that in this particular, in all these alignments we have Ai aligning to Bj in the last column, right. So, this is the last column of the alignment. Now, all we need is to look for the optimal alignment on how we can align the first I minus 1 characters of A to first j minus 1 characters of B. So, that is basically saying that I can write it as V I minus 1 j minus 1, that is the optimal alignment of A1 to I minus 1 to B1 to j minus 1, plus the score I would have to align Ai to character Bj. So, that could be a match, mismatch, that we do not know. So, depending on that we can define this recursion based on the definition of G. So, that is easy, right. So, this particular case is very easy because there are no space characters involved. Now, what about Eij? Let us recall the definition of Eij. So, in these Eij alignments, we are looking at those alignments that have the last column with character space opposite to character Bj. So, in this case the last column involves space character aligning to Bj, and then we have to basically give the score of this alignment based on what has happened before. Now, we have to keep this into account, whether are we starting a gap here or whether this is the gap extension, because depending on that we will be giving appropriate score to this alignment, right. So, for example, if this is a gap extension, right. So, for example, if this is the case, then I would assign the score of only a gap extension at this column, whereas if this is not the case, like for example, if my sequence AI is matching here, then I would start a new gap and I would need to penalize C1 plus C2 here, because I am starting a gap and I am extending it by one position. So, accordingly you can think of the recursion should work in the following way. So, if I am extending, that is if I already have a gap before on my, if I already have a space character on my sequence 1, then I should be using matrix E, and using that optimal score I can further extend alignment by 1 and I can obtain this score of E I j minus 1 minus C2. In other two cases where I am starting a new gap, there I would have to consider matrices G and F, because in those matrices there is no gap or no space character on first sequence. So, in those cases I would use the values from those tables and I would start and extend the gap as well. So, depending on whether we are starting a gap or extending a gap, right, we have to appropriately consider the values in the recursion. Similarly, the last value of Fij is going to work in the same way. That is, if we are just extending the gap by one more, that is the gap was started earlier, we are just extending it by one further position, then we are going to use Fi minus 1 j minus C2, and for other cases where we are both starting as well as extending a gap, then we have to use matrices E and G to further start and extend the gap. So, I hope this trick is clear on why we are able to use 4 matrices now, and with these 4 matrices we are able to give a recursion that is able to solve optimal alignment between A 1 to I to B 1 to J. So, between these two prefixes we have access to the optimal alignment score V I comma j, and ultimately if we solve the complete tables, then we would end up reporting V m comma n as output, which is the final optimal alignment between both sequences. So, just one last detail of dynamic programming is that we have to give the initialization, and initialization is easy depending on the definitions, because we just have to follow what definitions have we given for V, E, F and G. So, remember that if you have an empty string from A aligning to a prefix of B, then basically what we are saying is that we have a single gap of size j, right, because you will have to insert j space characters in order to match with j characters from B sequence B, and that would cost equivalent to a gap of length j, which is a single gap of length j would cost us minus C1 minus j C2. Similarly, if you have prefix of A aligning to empty string from sequence B, then again that is equivalent to saying that we have a single gap of length I, and accordingly I would penalize it by minus C1 that is single gap and of length I. So, therefore, minus I times C2. And finally, V0 comma 0, that is alignment of two empty strings, is going to give us score of 0. So, that is trivial, and all other values we can set to minus infinity because they are not relevant. So, for the dp to work correctly, we will set them as minus infinity. So, with this initialization and with this recursion, we can compute the entire tables G, E, F, V and solve this problem optimally. Eventually, once we have computed the entire tables, we can again do the trace back as we have done before, and through the trace back we can figure out what the optimal alignment was. So, from the score and trace back we can also construct the alignment between sequences A and B. Now, what is the runtime of this algorithm? Well, the runtime is trivial to analyze because all we are doing is we are filling 4 tables of size m cross n, and while filling these tables in each cell we are spending order 1 time, because all these computations, for each of these computations we require order 1 time to solve these values. So, we have order mn values to fill and each value requires order 1 time. Therefore, the total runtime of this algorithm is order mn, and which is fantastic because now we have achieved the same time complexity that we had for simpler problem where we were not considering gaps at all. So, this is a very useful trick of having 4 tables and still managing to solve this problem in the same time as we were solving for the previous methods. So, to summarize this part, we can say that the optimal alignment with affine gap weights can be computed in order mn time. That is the same time that we had required for optimal alignment without a gap term. So, all the alignments that we have seen, that is local alignment, global alignment, in all those alignment types we can include the gap term in the formulation and still solve the problem in order mn time. Now, this concept of gaps is significant because if you go to any alignment method, so for example, if you go to one of the popular methods which is BLAST, right. So, if you go to this website, you can open the alignment software and you will have multiple options whether you want to align DNA sequences or protein sequences. Suppose you click on aligning nucleotide sequences, right. So, if you go to the nucleotide sequence option, you will be asked to upload the sequence that you want to align. So, there if you, so you will have options to upload the sequence and you would have option to specify what do you want to align against, right. There are multiple databases there, and if you scroll further down, what you will see is that the aligner allows you to set various algorithmic parameters. So, for example, it will allow you to specify match mismatch scores, and it will also allow you to set gap cost, right. And again you can see that it will allow you to specify the cost to create a gap as well as extend a gap, right. So, this is now significant because for various applications you may want to set this parameter differently, and based on this lecture now you know what is the meaning of this parameter. So, I will repeat. So, based on this lecture now you would know the significance of what these gap costs mean and how would you want to set these gap cost parameters. Thank you.